Hello friends, AI product development means more than just shipping the features. It requires crafting intelligent workflows. So success requires more than just applying an LLM. It requires strategic expertise in concepts like memory management, multimodal orchestration, and the art of prompt fine-tuning. So today we will discuss all the key concepts from a PM's perspective. If you are a PM and you are working with the teams building AI, so today's video is going to be very relevant. So today we are going to talk about prompt engineering, zero shot versus one shot learning, short term versus long term memory, retrieval augmented generation, and multi agent systems. And finally, we are going to talk about how to evaluate the performance of your AI agent or LLM. So let's get started. So let's start with the prompt engineering. Even if it is too obvious to craft a good response and everybody knows that AI is as good as the prompt that is given to it or the instruction that is given to it, but still it's the most important concept or area you need to know when you are building a AI based pipeline. So I'll just quickly cover a few things over here to set the stage, and then we'll move forward. So from the prompt engineering point of view, you have to be specific. Then you have to use step-by-step instructions. So if you use step-by-step instructions, AI perform better with structured inputs. If you give it clear instructions, AI will give you the clear answer based on those instructions. And then few shot learning. So few shot learning we will discuss in detail in the section below. In the gist of it, few shot learning means provide AI few examples before expecting an answer. Basically, for example, if you want AI to sum two numbers, let's say you want to ask, okay, what is 4 plus 6? So you just give one example before it, like, okay, if 2 plus 2 is equal to 4, then what is 4 plus 6? So the chances of AI making an error over here reduces if you give few examples to the AI for your context. And you must have seen a lot of benchmarks when people compare AI models. They talk about one shot score and then basically few shot score. That would mean that, okay, how the AI performs if you directly ask the question, and how would AI perform if you ask the question by providing few examples to it. So providing examples to AI increases the accuracy of the pipeline. Then there are basically two types of prompts. One is system prompt and then other is user prompt. So what is system prompt? System prompt is a one-time prompt that you provide to LLM to set the conversation. For example, in a system prompt, I will give instructions like, okay, you are a assistant to a scientist and this is your roles and responsibilities. This is how you have to respond to each query that you are given. For example, you have to analyze at least 3 newspapers before giving an answer. So this is you give one time prompt to the agent to set the stage, like this is how you are going to perform, this is how you are going to act. For example, if you are building a support agent, then the system prompt will consist of some instructions around the language, how to greet the user, how to talk, what not to talk, what is strictly prohibited. So all such instructions goes into system prompt, and this is what the creator of the pipeline will configure generally. Then the second thing is user prompt. So user prompt is this query that your end user is asking the LLM, right? It's the same. Basically, if you are using Chat GPT, so whatever instruction you give to the GPT, it is registered as a user. So these are generally mainly two type of prompts used, right? So let's move ahead. Now let's talk about zero shot versus one shot learning. So okay, so there is a saying that, okay, not every AI model needs massive training. The right learning approach depends on your use case. So if you are, let's say, training an AI agent or building your own LLM, sometimes you can leverage the 80-90% of the result by just increasing the amount of prompt, like increasing the number of example you give to the AI agent. As I mentioned earlier as well, like it is seen that large language models generally perform better on a multi-shot learning over a zero-shot learning. So if you ask agent by giving few examples, it will give you better result, right? So this is generally the difference between zero shot and one shot learning. So basically you use zero shot learning when you need a highly generalized response, and you use one shot learning when you need a specific response in the way you need. So these are few examples of like when to use zero shot and when to use one shot learning. So let's talk about short term versus long term memory in AI pipelines. A GPT like model or large language models don't have built in memory. You give it one question or you give it one query, it will give you one answer in it. And that's how the, like, basically LLMs have been designed. So they are designed to generate the next words. So they don't have memory built in. So all the tools like Cloud or Chat GPT, they have their in like a wrapper of memory that they have designed on top of their suite. So basically you imagine it like this. So user enters a query. So along with the query, they will pass the previous memory manually to the LLM, and LLM will use that information as a context along with the user query to generate the next word. Basically, there are two types of memory. One is short-term memory. Short-term memory generally means session-based context. So basically, if you are using a travel website, right, and over there you are booking the ticket, you would want your AI agent to know the conversation. For example, the chatbot that helps book flight should remember the trip details only within the session. So if the user has said that, okay, book me a ticket, and LLM asks, okay, from where you want to travel, then user say, I want to go from Delhi to Goa. Then the agent says, okay, let me check tickets for you, and then replies with the available seats or available flights, and then user selects a flight. Okay, user says, okay, I want to book Air India this flight. But for the next response, agent should know that, okay, user is traveling from Delhi to Goa. So this is called short-term memory, like basically session-based context. So generally it is implemented by passing the whole context along with the each user query to LLM to generate the next response. Then there is a long-term memory. So long-term memory is the previous knowledge or some SOP, basically your process documentation that your AI agent needs to use before giving answer to the user. For example, if you are building a support bot, so for long-term memory, you would need some SOP. You would want your AI agent to basically follow some set of rules. So there are two ways. One way is you configure all those instructions in the system prompt that we discussed on in the initial section over here. Along with it, if you want to refer to some past tickets of the user and you want it to judge the user behavior. Okay, what kind of tickets user raise, or does this user raise irrelevant tickets often? So to build the context around the conversation, you need past data. So now you can't feed all the past data in the prompt. Generally, there is a limit to the number of words you can pass in the prompt, right? Or you need like how past similar queries has been resolved. Your AI agent needs to know how past similar queries has been resolved. So you need to know the context from the past tickets, from the past complaints, or your process documentation. For that, you need long-term memory. So it is best for relation-driven AI, customer support, and personalized assistance. So we'll go in detail how to implement long-term memory. So we will not go in detail how to implement short-term memory because it is just like caching the whole conversation in some database and then passing it along with the context to the LLM. So short-term memory is fairly simple to implement, and long-term memory, since it means dealing with a lot of context and lot of data, it is relatively harder to implement. It also matters over here, like what are you able to fetch the relevant data to the conversation. Also, we need to know that in the short-term memory, there is a problem of context window. So most of the AI agents, or even if you are using some API, they have like a basically limited context window. For example, Cloud is having around 200k tokens worth of context window size. So if you exceed the context window, your AI may lose the context, and then it can result into hallucinations. What I mean by that is, so let's say if in a long conversation, your AI agent is out of context, so it may ask the user, okay, from where you want to book the flight, whereas user has already specified that I want to go from Delhi to Goa. This is one of the limitations that you hit with the short-term memory sometimes, and it becomes evident when you are dealing in a long tail conversations. Like let's say you are trying to automate a email chain. Generally, email chains are very long. So it becomes little bit harder to maintain the whole context window in a short-term memory. So over there, you need a mix of basically you need to convert some of the conversations into your long-term memory on the runtime. So basically, it is less likely to happen, but still, as a PM, you need to know that okay, there is a limitation of context window, and your AI agent can't hold unlimited amount of context. So with this, let's jump into basically RAG, which is Retrieval Augmented Generation. First, let's discuss what is RAG and why is it used in the AI pipelines. So RAG is Retrieval Augmented Generation, as we discussed in the long-term memory. So basically your AI agent will first query some database. So basically let's say user has given a query. So your AI agent won't produce an answer straight away. It will first try to get some information from the database or any mechanism that you have configured, and will retrieve the related information from that database and then use that information to generate the response. So this is what RAG is. So why is it used? Basically, if as we discussed, AIs are good with multi-shot prompts. Secondly, if you want your AI agent to follow your business specific needs, so you can configure this approach where you ask your AI agent to fetch some business related SOPs, business related documentation, and then use that information to craft the next answer. Let's say you have an inquiry bot and you have a database of FAQs that okay, generally this is the answer to this kind of a question. So instead of your AI agent to give a generalized answer to a user query, you want your AI agent to first go through that database, fetch the similar FAQs, read those FAQs, understand the answers to such problems, and then respond to the user query. Over there, RAG based pipelines are used. Then let's discuss about the key components of the RAG. As I mentioned, RAG means retrieving data from a database. So first step is storing data into the database. But when you are storing data into the database, there are few things that you need to keep in mind, right? So you can't just throw all the data into a database and then expect your AI agent to fetch all the data and then basically generate an answer. That is not possible because there is a limitation of context window. So you need to fetch the limited amount of information. Or even if you can fetch a lot of information, you can like push or you can pass only a limited amount of information to the LLM. While storing the data into your database, it is very important to structure it in a way so that when you are pulling data from your database on the runtime, it is quick. It doesn't take too much time. So sometimes a lot of people are building voice bots. So over there, latency is a very crucial factor. Over there, if you need to use RAG, it has to be very quick. Even if you are building like chatbots also, your users might not want to wait for too long for your agent to respond. So it has to be quick. Secondly, it has to be factually correct, grounded. Basically, groundedness should be there. And it has to be contextually rich information to the user query, right? And third, it has to be cost efficient, right? It shouldn't be like costing very much because AI agent might need to query the DB a lot, right? Because there can be a lot of user queries happening on your support portal and or any portal where your AI agent is deployed. So over there you would want it to be cost efficient. So these are like broader goals that you need to keep in mind when you are building a RAG based pipeline. So over here, like there is a popular technique that most of the teams use is vector embedding. So why people use vector embeddings? Okay, let's discuss that. But before that, let's discuss what is vector embedding. You can simply assume it like that. Okay, you have a paragraph and then you convert it into a vector. Vector is just an array of numbers. Vector embedding means process of transforming data into that array of numbers which captures the semantic meaning of the data, so that when your user query happens, you can easily pull by comparing the user query. So how it happens is, so you convert the user query into the same dimensional vector, and then you compare the user query vector to each vector stored in the DB, and then you filter out all the matching vectors from the database. But why people use this method? Because there can be other ways of retrieving documents. Like for example, in the traditional search engines, how the documents have been received, like retrieved based on the terms. Okay, let's say I want to book a flight. So basically book flight can be two entities, and you can like basically match a lot of FAQs with this keyword. But we will discuss few limitations. Although this technique is also used, we will discuss it in the structured storage for keyword search section. But let's first discuss why people use vector embeddings. So as I have written, like instead of comparing keywords, RAGs use vector embeddings to find documents that are semantically similar to user query. Basically where the meaning of the query is similar. So for matching the meaning, not just the keyword, it is important to generate that embedding. Again, embedding is also generated by some large language model. So what embedding does is, embedding extracts out the basically semantic meaning. For example, there is a line in the database, okay, the queen passed this order. Then the user asks, what was the order passed by the parliament that implied this law? In your database, the term is queen. It won't match to the user query directly if you enable keyword based search. So, but when you do semantic analysis, right, these two queries might match. I'm again saying might match if they are semantically close in your dictionary, or if they are semantically close in your data set. So that's why, that is the first reason of generating the vector embedding, where you capture the semantic meaning of the information, and when you compare that with the semantic meaning of the user query. So again, this allows system to retrieve the most relevant information, even if it extracts the words that aren't present, leading to more accurate and comprehensive responses. And essentially, embeddings enable RAG to understand the intent and context rather than just matching the surface level term. Okay, I hope it is clear to you now that why vector embeddings are required. Because user queries are not in a well structured fashion, right? User will use a like layman language, normal language, I would say, that may not match by entities that are present in your database. So now if it is clear to you why we need vector embedding, so now let's jump on few key concepts while using the vector embedding. So first concept is of chunking. So what is chunking? So as I mentioned earlier, AI agents can't hold a lot of context, like you can't pass the whole book to the AI agent. And to make it cost efficient as well, you need to pass only the relevant information, right? So to enable that, you need chunking. So chunking is splitting your very big dog. Let's say you have a book, then you're splitting your book into smaller chunks. So chunk is one small piece of information from the whole data. So you divide your data set into smaller pieces or smaller chunks of data, and you feed those chunks into the database. And at the time of retrieval, you fetch the most relevant chunks of the database. You don't fetch the whole book. You fetch the relevant paragraphs of the book. Since I mentioned like, okay, chunking can be at multiple layers, right? So let's say you have a book. So you may chunk at a chapter level as well. Someone may want to chunk things at a page level. Someone may want to chunk things at a paragraph level. So the chunking approach that you are going to take matters a lot in the efficiency of your RAG pipeline. There are two things that we need to know. One is chunking size considerations. So let's say you are feeding the code to the AI. So over there, you would need one class to be present in one chunk. Versus if you are basically dealing with the database of FAQs, you may keep one FAQ as a one chunk. Or if you are dealing with chunking a novel, maybe you can keep one paragraph as a chunk, right? So chunk size means determining the optimal text segment length. And then the second thing is text splitting. So basically, what is text splitting? Text splitting is the method of dividing documents into meaningful chunks. So let's say you are chunking a book, right? So you may use sentence splitter, which will use full stop as a basically delimiter to create to separate out sentences from each other, and you will store one sentence at a time. And let's say you are using paragraph chunker, so basically it will use new line as a basically delimiter to separate out your paragraphs from each other, and you will create one paragraph as a chunk, right? And if you are, let's say, chunking basically splitting a HTML doc, then maybe you can use divs to separate out different chunks, right? Basically, one div can be treated as one chunk. Basically, text splitting techniques consists of all the techniques by which you can divide your document. Like, for example, paragraph. Let's say if you are splitting basis pages, then maybe like word like PTO can act as a delimiter, and you can basically chunk based on that. I'm just giving basic examples, not going too deep into this. Then coming to embedding models. Okay, now let's say you have chunked your data. Now your data will be passed to an embedding model, which will project your data into a vector space. So generally, a vector space is fixed in size. For example, a lot of encoders use like output 1500 something size of vector. Basically, if let's say you have a paragraph, now there can be a lot of meanings of the paragraph. So choosing a right model matters, because there will be some information loss. Let's assume it like this. So you have a paragraph, the paragraph can be interpreted in a lot of ways, but you are now projecting it to a constant 1500 space. And let's say you have like more than 1500 words in the paragraph, then some of the meaning has to be lost. So choosing the right embedding model is very, very essential. Right? So there are like different kind of models who that pay like basically attention to different kinds of words. It depends on your business use cases. For example, if you are using, like, let's say if you are using your data set to classify issues, then maybe something like encoder only models work good in some in those scenarios. There are a lot of research on models like modern BERT. These are encoder only models and are very good for classification kind of tasks. But you can basically try different models, or your teams can try different embedding models to see the performance of your retrieval. Now the third thing that is very less talked about is chunk enhancement. So what is chunk enhancement? So let's say you are chunking a paragraph. Your paragraph on its own might not capture the whole context of the chapter, or maybe your paragraph can be interpreted differently outside the context of the chapter. And when you retrieve your paragraph independently, it might not match with the relevant queries. In chunk enhancement, what you do, you enhance each chunk to contain the context information and associate that context with the chunk. For example, if you are chunking the chapter and you have a paragraph, you will append the summary of the chapter with the paragraph, and then you pass it to the embedding model. Now it is seen, if you enhance chunks and add context to the chunk, it reduces the wrong retrieval. Basically, it increases your precision, right? And error rate reduces. These are like main key concepts that are used when you are storing the data into the vector database. Again, I'm only talking about vector database. So this is the pictorial representation. So if you see, like, you have text, and then basically you have text cleaning, then you are tokenizing the text, and then you are chunking the text. So tokenization and So text cleaning is something you can do sometimes if you already have clean text, then you may skip. Then chunking, then chunk generator, you have lot of chunks, and then basically metadata extractor, you then embed them, basically you then append the metadata, then you pass it to basically embedding model generates the vector, and which is then stored into the vector database. Again, so this is semantic matching. When you are storing data into a vector database, you are primarily doing it for semantic matching. Sometimes semantic matching is not sufficient enough. Sometimes you have to match exact keywords. So over there, your old Elasticsearch like storage comes into play, where you store data into a traditional database like Postgres or Elasticsearch, and then you do like basically term-based search. So along with the vector databases, teams generally use your Elasticsearch, etc., to enable the term-based search. So this is also very important and is quite often used in the industry, where you store the data in a traditional DB for keyword-based search, along with the vector embedding for semantic search. So let's look at the complete diagram, then we will jump into the retrieval part. So you have a document, then document text extraction, then BM25 processing. BM25 is best match 25. Okay. Then you have vector processing. Over here, term frequency analysis, and then inverse document frequency, like, okay, you associate documents with each term. Let's say you have a term, review. Then you associate all the documents in which review comes with this term review. So when a search query happens for review, you immediately return all the documents. Okay. So this is how broadly BM25 or term-based search works. So then vector processing, embedding creation, and when you have embedding creation, you store it into the database, and then your database is stored into your vector DB. And when user query happens, then you search on both, like basically your Elasticsearch or Postgres, where you have stored your term-based data, and then you also search over the vector DB, and you merge the results. And then there is a special technique of merging that is called reranking. We will talk about it later. So till now we have discussed how to store the data in the database. Let's jump into another next section, which is retrieval. So let's say you have stored the data into database most efficiently. Now you need to fetch the data from the database. When you have to fetch the data from the database, you don't generally send the user query to the database, because it doesn't give you all the relevant documents. You use few techniques to increase the recall. Basically, what is recall? Recall is like how if you have, let's say, 100 documents and you do a search, how many relevant documents are you able to fetch? Let's say if there are 70 relevant documents to a query and your search is able to fetch only 30 or 40 relevant documents, then your recall is 30 divided by 70. So there are techniques with which you can increase your chances of hit. So basically, first is query enhancement techniques, as I mentioned, like you modify the query a little bit so that your chances of hitting the relevant document increasing. So in this case, first is query expansion. So what is query expansion? So query expansion is a technique when if let's say user has said how to reset a password. So basically you expand this query into multiple queries. So basically one way of expanding could be add synonyms, basically password reset, change password, update credentials, right? Another way of modifying this query can be context addition. For example, account security, login issues, authentication. Third type of expansion can be based on troubleshooting, help request, security action, right? Intent basically, because intent is of seeking help. Right. So basis that documents related to troubleshooting can also be relevant documents, right? That's why I was saying, like when you directly send this query to database, sometimes you fetch only 30-40 out of let's say 60-70 relevant documents. Then basically extract entities. This can be used with to perform the term-based query as well, password, account, authentication system, etc. Basically you generate all the queries. Then you have generated all the queries, you send all the queries into over the vector DB and search for all the basically search against all the queries. And when you retrieve all the documents, you then use Reranker to merge the documents retrieved by all the queries, because a lot of these queries will generate duplicate documents, right? Then you will need to and you will not be interested in so many documents, because let's say now if you are seeing over here there are 12 queries and each query is say retrieving 10 documents, you are getting 120 documents. If you are passing 120 documents to LLM, it is going to cost you a lot of, so you need selective information which is most relevant. So that's where result aggregation and re-ranking comes into picture. We'll talk in a bit. So, but in broad, with this, I think this is very clear example how query expansion works in practice. Then the second term or second concept of enhancing the query is query decomposition. So what query decomposition means is when you break a large query into smaller queries, and then you fetch the results for those smaller queries. I'll explain how. So let's say someone asks compare the price and features of enterprise versus pro plan. Okay. Nowadays, like a lot of websites may have direct comparisons out there in some blog form or so, but maybe they are not present, right? So it will basically break this query into multiple queries. For example, what is the pricing of enterprise plan and what is the pricing of pro plan? Then it will break it into feature wise query. What is the features included in the enterprise plan and what is the features included in the pro plan? Because the direct comparison of price, of features, of integrations might not be available in the dataset. But if you execute the query, execute two queries separately, like okay, you fetch all the data of pro plan and then you fetch all the data of enterprise plan, and then you compare the data, you may end up resulting the better result, right? Again, another example I generally use when I explain this concept to people is like, let's say user asks which country make more money in software, India or China. Maybe the direct answer might not be available in any articles or newspapers or etc. But there might be a lot of articles where India's income in software industry is stated, and there might be independent articles in some Chinese media where China's income in software industry might be specified. And if your query is able to break main query, like who made the more money, India or China, into two queries, how much money India make and how much money China make, it might be able to retrieve the relevant documents. So you are recalling pages. I hope query decomposition is clear. Then basically the hypothetical doc generation. So this is again another technique where you generate a similar doc to the user query. For example, let's say user asks for the cancellation process. Then you will generate a doc which will look like a SOP of cancellation process. Okay. So now, since a hypothetical doc of cancellation process will contain most of the terms that would be present in the actual doc, so your chances of hitting the relevant documents increases by manifold. So what hypothetical doc means? You generate a hypothetical doc against a user query, and then you again chunk that doc, and against each chunk you generate embedding, and then you fetch the result against each embedding from the database. So this again increases your chances of hitting all the relevant documents. So these are like three techniques. There are many other techniques that you can use to enhance the query. And then you have a hybrid retrieval techniques, basically combining the semantic and keyword based retrieval for high accuracy. So these are majorly retrieval techniques, how to retrieve all the relevant documents from the database. Okay, cool. So initially you had stored all the information in the database. Now you have learned how to retrieve the information out of the database. Then the third thing is re-ranking. Since you have retrieved a lot of documents, but to make a decision, your LLM might need a handful of those documents. Maybe a lot of documents contain the same information. So what a re-ranker does, re-ranker filters out, let's say top 10 or maybe top 5 documents which are most relevant to the user query. And how and why and how of this is, basically when you generated the embedding, you just projected your document over a vector of 1500 or 1600. You at the time of generating embedding, you didn't know what kind of query user is going to execute, right? But now re-ranking, in re-ranking, you have actual query, you have actual documents. Now, basically, a LLM can compare the query with the actual document. So that's why also re-rankers are slow, because it has to do a lot of comparison. Basically, it has to compare the actual query with the actual text, English like text. Comparing numbers to numbers is fast for a LLM, because it is like executing a cosine similarity function, which is very fast. So retrieval is generally very fast. Re-ranking is slow. So let's say you have filtered out top 100 documents out of like your document database. Now the task is to find top 10 documents, which is generally slow. So first people do like statistical re-ranking. So what I mean by statistical re-ranking is you use techniques like stats. Let's say if a lot of queries are producing same document, let's say you simply calculate, okay, in how many queries this document was returned, and the documents that were returned by a lot of queries will get higher rank. And first you rank documents basis that. If a document is matching to the semantic meaning of a lot of queries, that means there is a high probability this document is relevant. So once you have statistic basis ranks, then you like basically use that directly to retrieve top k documents. Another technique that is quite used is model based re-ranking, where you ask some LLM to give you top 10, top 20 documents. Generally, LLM based re-ranking is slow. Let's say now you have given 30 documents and you ask LLM to give top 10 documents. It will give you, let's say, 1, 2, 3, 4, 5 documents. But if you again execute the same query, it might give you another set of documents which it might think are more relevant, right? So model based re-ranking has its own challenges. As I mentioned, it sometimes returns different set of documents if you execute, basically if you call the LLM with the same query and same set of documents, right? So there are techniques to avoid that. For example, you send documents in pairs, but at the end of the day, it increases your number of calls to the LLM. So people generally try to keep these things simple enough. So this is all about re-ranking. So these are the main building blocks of a retrieval-augmented generation. One is storage, another is retrieval, third is re-ranking. Now let's jump into the performance metric, how to measure the performance of LLM. Our first metric that is most widely used is precision. Let's say you have fetched 10 documents. Out of those fetched 10 documents, how many documents were relevant? So let's say you have fetched 7 relevant documents and 3 irrelevant documents, then your precision is 7. Then the second metric that is most widely used is recall. Basically, if let's say there are 100 documents and you are executing the query and you know there are 70 documents that should match my query, but at the end of the day you are only able to fetch 30 documents. So your recall is 30 by 70, because you are able to fetch only 30 documents and 70 documents you should have fetched, which are relevant documents. Recall is generally a metric of coverage. Third is F1 score. F1 score is basically harmonic mean between recall and precision. So it will ensure that you are balancing both. Sometimes precision is good enough, but recall is not there. You are trying to fetch only 20 documents. You are able to fetch 20 documents, which are most relevant documents. So your precision is 100%. But there are 60 documents which are relevant in the database. So F1 score generally balances the precision and recall. Then there are other metrics as well, like, okay, what is the rank of the most relevant document in the list, etc., etc. But these are like major matrices that most people will use while measuring the performance of a rank. And then there are latency and efficiency matrices, basically to see that how much time it is taking to fetch all the relevant documents. Cool. These are most of the techniques, most of the basically concepts that you need to be aware of. Now I'm going to give you a tip. So basically, whenever you are building a RAG, start with very small data set. Pick one document type, for example, FAQs, and build for that, get a win, and then introduce another document type. If you start building with all type of documents, you are going to get confused. There is a high probability. If you focus on one type of documents, For example, FAQs. Your chunking is simplified. Your chunking technique is simplified. Your choice of model is simplified. Your expansion strategy is simplified. You start with one document type and then expand from there. So yeah, this is about RAG. And then let's talk about multi-agent systems. So as we discussed, where RAG shines is when you have a lot of information and you can't pass all the information in one go to the LLM. And you need to fetch the information on the runtime from the database. But now let's assume you are building a bot for e-commerce website. And there are a lot of intents from order booking, order cancellation, FAQs, ratings and reviews, delivery, refunds and replacements. And if you build one bot who is doing all of this, the chances of hallucinations increases by a lot basically. There is a high probability that customer is talking about refund and replacement and bot considers it as a cancellation type of a query. There are high chances customer switches the context, but bot is holding off the old context only. Now you imagine you have a prompt where you have defined all the rules for all type of scenarios, all type of intents, and now you have to modify it for one intent. And you see after modification for one intent, some another intent starts to break. You try to fix for that intent, some another intent starts to break. Even if you introduce RAG, that you have to fetch this data on the runtime from the database, there has to be a certain prompt that you have to pass. Basically, if you pass too much information to the bot, sometimes it starts to confuse and it starts to hallucinate. So to reduce the hallucinations, to have more control over the flow of the bot, people use multi-agent systems. So what multi-agent systems do? So you have a different bots. For example, you have one bot for orders. Basically, you have one bot for cancellations. You have one bot for refunds. You have one bot for user inquiries. You have one bot for reviews. You have one bot for deals. And then you have a central orchestrator that will understand the user query and then pass it to the relevant bot. So now you have replaced one bot with the army of bots, and each bot is specialized for one kind of task. And now if you want to modify, let's say you want to modify the flow for orders, refunds. Now all of your other bots are protected from the change. You are just changing one bot. And now if you want to implement some business logic in between as well, you can write your business logic in the code form as well in the workflow of multi-agent architecture. So let's discuss these points in brief. I have explained from the 2000 feet view POV. So RAG is good for information retrieval, but what to do when you have too many intents? Prompts become too large, bots start to mix the scenarios. And to reduce hallucinations and have more control over the flow, and to have guided flow, you need multi-agent architecture. And if you see a lot of tools like Diffie is there, most of open source tools, if they are good, will have multi-agent architecture implemented in one way or another. And it also helps you in reducing the cost. Basically, now if you have a long prompt, you had one bot, right? You have passed the information of all the scenarios to the bot, which is irrelevant if the user is just interested in cancellation. You are just passing extra tokens to the LLM for order place, like for placing the order, for reviews, etc. That all information is irrelevant to the bot for refund query, right? So now with the multi-bot architecture, a lot of cost is reduced because you are just passing the enough or required information to the bot, right? Or the bot containing the required information gets activated, in other words. So over here, key concepts to know is basically task specialization. Each agent focus on their specific functions such as classification. Some are for data retrieval, some are for decision making, and some are for execution. And then in execution as well, there can be different roles. And then with multi-agent architecture, you can also do parallel processing. Cool. So what parallel processing means is, let's say for a particular user query, your bot needs to check two systems. So one bot can check one system and another bot can check another system at the same time. You can basically have a parallel processing kind of a setup as well. Then agent handoff. Basically, if first agent has detected the query as order cancellation query, how efficiently is it able to delegate this query to the cancellation specific bot? And then basically parent handoff. Now let's say user changes the intent. User asks like, okay, I had another order where I want to know the status of delivery. User was earlier talking about cancellation of one order, but now it suddenly switches to the delivery related intent. So the child agent should be able to pass the context to the parent so that parent can again redirect it to the delivery specific agent. Your bots need to coordinate with each other, and this is sometimes error prone, right? Sometimes bot fails to detect intents. Sometimes bots fail to detect that okay, the intent has been changed. So testing from the PM's point of view, testing the agent handoff is very, very important. Again, this is an example. So basically in a e-com website, for example, so you have multiple touch points. Your customer might be reaching over the email, your customers might be reaching over the chat. Then the customer's message land over the intent router. Basically it classifies the intent, then it passes it to priority agent, and then basically one agent is for billing, one agent is for technical issues, one agent is for product specialist like product info or comparisons, etc. One agent is order agent, which is like specializes in tracking order, processing returns, etc., etc. So as you can see, right, each agent is doing its own job. Billing agent can handle billing efficiently, order agent can handle orders efficiently, product specialist can give information about the product or comparison, and basically a central controller agent manages all the orchestration, like which agent will get activated, if user switches to another query, then basically this child agent should be able to redirect the request to controller, and then controller should be again able to land the request to a new child. So this is the broad diagram of how the multi-agent architecture works. Cool. Now let's talk about the last concept, which is evaluation of LLM. Now there are two broad ways. One is qualitative analysis and another is quantitative analysis. So in qualitative analysis, you do human in the loop assessment. So you ask some expert to check the performance of the bot, and basis their experience and industry expertise, they give you the basically score of the bot, or basically give you the detailed summary that where it is doing good, where it is doing bad, in which intent it is doing phenomenal, in these are the intents where this bot is not giving the correct result, right? That is qualitative analysis. Like for example, human in the loop assessment, where experts review the and refine the system generated outputs. Then the user feedback integration, where you have NPS like a score, NPS kind of a score for the bot, or CSAT kind of a score for the bot, and based on that score you can do the qualitative analysis of the bot, like how helpful is the bot. Then you have a quantitative analysis, where against each query the generated response is passed to a judge, which is again a LLM, and you ask the judge that okay, if the answer given by the bot was correct or not, and then based on that you assess the score. You compute a score, like okay, out of 100 questions, how many questions was the bot able to answer correctly. And then maybe sometimes you have to reduce the cost and you are trying multiple bots, and then you can compare the results produced by both the bots by using LLM as a judge. Basically what you do in that case is you fire the same query on both the bots will generate the answer, and generated answer will pass to LLM, and LLM will tell which answer is better. So all of these techniques are used in the quantitative analysis of the bot. And similarly, A/B testing can also be done by using LLM as a judge. So from a PM's point of view, you should be aware of LLM as a judge, and how to use LLM as a judge, how to do A/B testing by using LLMs, when to do quantitative analysis and when to do qualitative analysis. So you start with the qualitative analysis. When you have initial confidence, then you ask your teams to build a quantitative framework. So first you start with the qualitative framework where you know that your bot is okay in 70-80% of the cases is giving right answer, which is actually correct, which is uh, which incorporates ground reality. And then when you have such a bot, then you do quantitative analysis of the bot. I hope all of these concepts are now clear to you, and I was able to add value. And thanks for watching. Thank you.